Good afternoon, and welcome back to the Livestock Heat Stress webinar series hosted by the USDA's Agricultural Research Service. My name is Maribel Alonso. Today, we have section 2 of the webinar series. A few reminders before we get started. During the webinar, you will be muted. If you have any questions, please select the Q&A option on your screen. Dr. Jody Purswell, our presenter for today, will respond to all questions at the end of the presentation. All sessions of this webinar series will be recorded and available at the webinar's landing page. Now, Dr. Stephen Moeller, National Program Leader of Food Animal Production, will be introducing today's speaker. Dr. Moeller, whenever you're ready.
Thank you, Maribel, and also thank you to all of our office communication staff for helping us pull together our heat stress webinar series, and our scientists within USDA who are doing the research to help us mitigate heat stress, which we know is a major challenge right now, literally in the U.S. as we think about the heat that we're feeling here into early August and supposedly now, I suppose, through the whole month, it sounds like. Today, I'm happy to introduce Dr. Jody Purswell, who will be presenting on improving environmental control and building design for heat stress mitigation in broilers. Jody Purswell currently serves as a research leader of the USDA-ARS Poultry Research Unit in Mississippi State, Mississippi. He joined USDA-ARS in 2005 after receiving his PhD in agricultural engineering from the University of Kentucky. His research program is focused on development of improved housing design and environmental control methods, improving energy and water use efficiency in poultry production facilities, and developing climate change mitigation strategies for poultry producers. With that, we'll turn it over to Jody, and he'll present for us today. Thank you all for attending.
Okay. All righty. Good afternoon, everyone. Appreciate everybody that's here to discuss our research with you. This is an area of research that our lab has been working on since its inception in 1964. Of course, it's taken many twists and turns and evolved quite a bit in that time, but still the basic premise is there is that we want to improve environmental control, improve energy efficiency, and ultimately improve production and welfare for the poultry that we house. So a little bit of structure to what we're going to do today, talk a little bit about the background, particularly some of the work that's been done here from a historical perspective at our place, but then also look at what the effects of that research has been out in industry and where it's been applied, and then also look at how house design and ventilation system performance, and particularly the effect of inlet design on cooling and water usage, how all those tie together. This is not a new problem that we're addressing here, and it's been a research topic since probably the 50s. And of course, again, it's evolved somewhat since then, but the basic premise is that chickens are not as well equipped to deal with heat as, say, some of their mammal cousins in some of our other industries. And so we have to take particular note of that and do some things a little bit differently and approach it in a little bit different way to make sure that they stay as cool as possible and maintain welfare and productivity. From the physics standpoint, and I'm going to talk a little bit about physics. I'm an engineer, so that's how I communicate. But the biology here is very simple. The birds eat, and through metabolism generate heat. Of course, I think anybody that deals with animals understands that. But how we remove that heat is where the physics comes into play, and where building design really shines, as opposed to the limitations of say a feedlot where we don't have the amount of tools. Birds are typically raised indoors, and so we have a lot better control over their environment through things like ventilation, heating, and cooling that we don't have in other avenues. So we tend to look at the three classical heat transfer modes. So conduction, so a bird sitting on the ground, heat is going to flow from the organs and core of the body through the outer tissues, through the skin, through the feathers, and then into, say, the ground where they're sitting. Convection, when a fluid is flowing over a heated object, that heat loss is going to be proportional to that temperature difference. And then, of course, radiation. That's not really a big player, particularly for a market weight broiler, because that's temperature differences between the surroundings and the bird itself. And typically, those two are going to be fairly close together. And so we don't get a lot of transfer that way. There's still some, but it's certainly not the predominant avenue. And then, of course, because we're talking about biology, evaporative heat loss is always an improvement on top of the other three methods. And of course, birds don't sweat. They're not like humans or horses. And so really their only avenue for evaporative heat loss is through respiration. And that's limited because to really get, I don't want to say efficient, but maybe more effective evaporative heat loss, they have to pant. And of course, from the production side of things, panting requires energy, which burns feed. And so, the best, the best of both worlds is to do a really good job at improving conduction and convection, heat loss that way, and try to minimize that evaporative heat loss. And we do the best we can with the systems we have, and hopefully future research will help us get to a place where we can do that even more efficiently. Heat loss, regardless of the mode, is going to be limited by our ambient conditions. And as we face climate change, when we look at variability, potential of increased rate of heat waves, that makes mitigating heat stress as we go forward, and particularly in building design, ventilation system design, much more challenging. And so we need to make sure that we have capacity to kind of future-proof against those changes, but then also not go so overboard in that we make it economically unsustainable. One of the drivers of this that has sort of been a blessing and a curse is that, with our modern genetics, the growth rate is vastly improved, performance is improved, birds are more efficient, but then also metabolic heat production has also increased. I know my friends out at the Meat Animal Research Center a couple of years ago looked at swine, looked at heat production in swine and saw that gone up, say 15 to 20%. And of course, that was compared back to data from the 1950s. Our most recent data in broilers is from the 1980s. And of course, we've seen probably more genetic improvement in broilers than in swine, and at least on a relative sense. And so my guess is that we're looking at that level of change, maybe a little more. I'll talk a little bit more about that later in the presentation. So when we look at convection heat loss, we're dealing with a couple things. We're dealing with an increased heat production rate. We're dealing with warmer temperatures, and then of course just the basic things: air velocity. What's the speed of air flowing over a bird? What's the temperature differential? Again, driven by warmer temperatures, and what's the conductivity within the bird itself, and those changes in genetics. So here in the bottom right hand corner, there's a plot from some data that was generated back in the mid 80s. Over in England, and they looked at air velocity at 200 feet per minute on a hen, which isn't really a great predictor of what we see in a broiler, particularly given the age difference. But what we see is that there is a limit of what convective heat loss can do. It won't always be ever increasing. It goes up to an asymptote, and we really don't know what that is and what that looks like for modern birds. But basing that on what we know air velocity typically is in a house, at bird level, between 600 and 800 feet per minute, depending on how the building is designed and ventilation system is, we can see that we can remove, using this data, around 20 BTUs per hour per bird. That's right at the limit of what the bird produces, probably actually a little less than. And so again, this is where heat stress comes from. We can't always reliably cool, particularly in the case of a broiler house, we can't cool every bird super effectively. So we have to sort of work on the average and do the best we can. And, historically speaking, back in the 50s, folks were looking at, say, 300 feet per minute and saw that was beneficial in hot weather. But by the same token, 500 feet per minute was harmful. Of course, given the genetics and management styles of the time, that was probably correct. As we moved into the 60s and saw some genetic improvement, the design of a broiler house was beginning to come a little more solidified, a little more uniform. Air velocities got up to the mid 500s and did a good job. And really things kind of stayed static from there. And of course, most places were still cross ventilated, many naturally ventilated at that time. So that air velocity was really more of a sort of a pie in the sky target at that time versus a real sort of management strategy that folks used. In the 1980s, as I referenced in the previous slide, we really looked from the mathematical perspective. How does a bird generate heat? How do we lose that heat? How can we use that to inform ventilation system design? And that really went right into the 1990s there, looking at higher air velocity. Folks recognized the limitations of natural ventilation, recognized the limitations of just stir fans, and saw that we really needed to do more to really get these birds comfortable during hot weather, particularly here in the what we call the broiler belt. And those conditions are much different than what we see, say, in England, where that previous data was generated. And so, 400 feet per minute was really the general recommendation for most of the 90s and into the mid 2000s. And that's when our lab really got involved in air velocity research and looked to see where we could take it and where it would go. So the basis for our environmental control research here at our unit really is landed in two facilities. We have been doing this work since 1964, and our facilities we have a climate chamber building, and so we got 10 chambers that are fairly large and can do the temperature response work, and those have been functioning for quite a long time, and they're sort of our crown jewel in terms of research facilities, and we're excited that we can still crank out good data from that, and that really helps us inform really the next step of that type of data, which is going to our wind tunnels. And we've got a wind tunnel facility, picture on top there, where we can hold a couple hundred birds and have 2 tunnels plus some still air pins. And so we really use that to as much effect as we can. And so ventilation research here has been ongoing since the early mid 2000s, and really a lot of the ventilation recommendations that the broiler industry uses today come from our research. We have great partners in the extension world at different universities that use our data to help coach and teach people how best to ventilate broilers, and base a lot of that teaching off of the data that we generate in our facilities and publish in the scientific journal world. So really the first study that kind of put that facility, not necessarily on the map, but certainly brought attention to what air velocity could do in what I'd call the modern age, is looking at high temperature and high humidity conditions. And of course, that's what we tend to experience here in the South and in most of the broiler belt, anytime from April through the end of September. And really what we see here is gains for birds under 600 feet per minute, pretty significant increases there in gain, but also concurrent reductions in feed conversion. And while this was really geared towards, say, the productivity aspect of it, production efficiency aspect of it, what we have to keep in mind is that a bird that's suffering from heat stress, any animal that's suffering from heat stress, there's going to be a significant component of appetite suppression. And so a bird that's cool is going to eat more frequently. And so that's really borne out in this production data. And as you can see, birds that are essentially sitting in still air versus birds that are at 600 feet per minute, we're looking at a feed conversion of 4 pounds per pound down to 3 pounds per pound. That's a huge difference. And this data really frames what we're going to talk about in a few more slides when we start to look at velocity distribution and what that looks like in a real house. When we start to scale out how velocity changes in the house or distribution in the house, it's not necessarily uniform. And so this data can really help us put a good number on what our average gains and average feed conversion should really look like in those situations. So one of the questions that really came from that first study is, okay, we know what levels that air velocity needs to be, but how does that change according to bird age? How's that, and really how does that change according to bird size, bird weight? And so when we look at that, what we see is that up to, say, 42 days, there's not a lot of difference between 400 and 600 feet per minute. However, when we get to 43 days and beyond, as those birds really kind of kick into high gear in growth, particularly with these modern genetics, they sort of wake up one day and say, hey, I'm hungry, and really take off. And that period is where we really need to pay attention to air velocity. And so what we see is that gap widens significantly at that point. And of course, we're growing birds up to, say, 63, 64 days now, with much larger target weights than at this time. So it becomes even more important that we have proper air velocity and properly operating cooling at the same time. Again, it goes back to appetite suppression, or maintenance of appetite, maintenance of feed intake. When birds are not getting much air, particularly, and these are fairly moderate temperatures, there's still a big difference there. We're still looking at several points of feed conversion difference. And again, hot birds don't eat, and hot birds are heat stressed. So one of the extra tools that came out of a lot of this research is recovery ventilation. And of course, this is a common practice across the broiler industry now. We call it nighttime ventilation, but really what we're doing is trying to help those birds recover. When we look at data from feedlots, for example, it's typically whenever you have a heat wave and your temperatures don't get below a certain threshold, a day of that's not bad. 2 days of that is not great, but it's not terrible. 3 days of that, we really start to see a problem. And it's the same with birds. If we don't find a mechanism to shed that heat as temperatures, are prolonged highs, then we start seeing, obviously, we see mortalities, but then we also see big changes in production. And we're looking at nearly 3/4 of a pound gain between birds that are sitting in still air with no means of recovery versus birds that have really great air velocity for 24 hours straight, really helping mitigate that. And what's interesting about this was done at a fairly moderate temperature, a high of 86, which is for us down here in Mississippi and Alabama, South Georgia, that's fairly atypical for a daytime high, particularly in July and August. So again, as we scale that up to an even hotter environment, these changes that we see from this recovery ventilation are going to be magnified. So again, we had improvements in body weight here, improvements in feed conversion, about 25 points in feed conversion. That's huge. When we look at what the cost of just 1 point in feed conversion change to a typical broiler complex, those are huge feed costs that we can reduce simply by a very simple go in, heat waves come and go and lock on the fans. Fairly simple management strategy that gets us a lot of benefit. And so that sort of begs the question is, okay, is that really the optimal way to do that? And that's part of our research, current ongoing research, is that, that may be a little too big a hammer to use to go and lock everything on. And maybe we need to start adjusting that based on outside conditions and how do we do that. And so that's something we're really excited to take on and work on for the next few years. As I mentioned earlier, velocity distribution is an important part of what's going on here. Many people think in terms of average house velocity. Well, this house is designed to run 800 feet per minute, 1,000 feet per minute. And that's true probably in average, but when we look at where air is actually flowing and what it's doing inside a house, that's where the differences really start to get magnified. And so, in a typical broiler house where we've got evaporative cooling pads on one end and they're on both walls, and then down at the other end we have fans, and we have fans on opposing walls, we really see a big difference in what velocity distribution looks like. And really what we see is that about 25 to 30% of the house is at a very low velocity. And when we look at static pressure along the house, that really tells the story. When you see that large increase, it happens starting about 75 feet and goes out to about 125 feet. We're going from around 0.05 inches of water column up to around 0.13, 0.14. That's that last half of the evaporative cooling system. That's where the vast majority of the air comes in, that last 1/3 or 1/2 at a very high speed. And of course, that limits the effectiveness of cooling as well. And then we don't really see a lot of increase down the length of the house until we really start getting to the end, where we start to see changes in fans, some obstructions come into play. But this is something to keep in the back of your mind, and you'll see this plot a couple more times through the presentation. But again, when we start looking at, okay, these birds are in still air, these birds are in very high speed air, and these birds are somewhere in between, we can find just about all of those velocities in that house. And so when we're at 25% of the house is at way less velocity than what they actually need, we really start looking for solutions to help improve airflow in those areas, and thus improve cooling and maintain appetite and productivity and welfare. And so that's something that we're working on, and we'll continue to work on over our next upcoming project cycle. And the driver of all of this is fans. This is probably going to take a little bit of a departure from the other presentations, because it's a little more facility based rather than animal based, but it's an important point, I think, for everyone to understand. Much of how we design buildings is it's on paper. We can't go build a broiler house and try a bunch of different fans on it, find what we like, change the cooling system and get to where we want to be, and then say, okay, build this, and then build a whole bunch more. That's not really cost effective. So we have to really rely on, what I call conventional design techniques. But what we're finding is that, when we were designing for buildings that went to, say, 400 feet per minute of air velocity, everything sort of held what we expected to do, and the fans performed how we expected to perform. Once we got past that level and got up into the 600, 700, 800, even up to the 1,000 and 1,200 that we see in some facilities today, those rules of thumb don't really apply anymore. And so we really have to start taking a closer look at what fans are doing in the field and try to scale what we do from that. Most of our stakeholders, most of our poultry house growers, when they look at fans, they're relying on laboratory data. And laboratory data is essential because it allows us under fixed conditions to compare performance of fans. Because there's really no other way to do it. Because the static pressure in a real building is difficult to model, it's very difficult to predict. Just the computational power for that alone is pretty significant. So what we see is that installed performance varies pretty dramatically from laboratory values, and that's not unexpected. But I think the level at which that departure occurs is not well understood, and probably not as well publicized as it needs to be. But we're typically at 15% or more in terms of reduction from laboratory data. And the plot here on the bottom right really illustrates this. This is from some data we took about 5 years ago, and is published. We see that those solid round dots, that's the best lab test data there. We are only in a couple of instances are we really anywhere close to what that data says. And in some cases, there are some pretty significant departures at the same pressure. In fact, at around 55 pascals, what we see is we're almost at 40,000, probably around 36,000. And we can, see a real fan that's down around 25,000. That is a huge departure. That's certainly more than 15%. And what that means in real terms is that we are expending the energy, burning utilities, using electricity, and only getting a portion of what we think we're getting in terms of the design. And part of that's due to the operating pressures, part of that's due to fan arrangement, and part of that's just due to manufacturing tolerance. And there's not a lot we can do about that particular part, but I think there's ways we can optimize what's going on in the house with some design changes that we're currently studying. So the pressure characteristics, as I alluded to in the slide before, they're very difficult to predict. They're very difficult to model. And there's not really a good way to do it without expending a lot of computational power to do it. And again, that's work that will be ongoing in the future. But at this point, we're still really not at the point where we can do that effectively and reliably. But static pressure is the load that a fan has to work against. It's like any other thing. It's like driving a car down the road. The energy that needs to be expended to get that car moving and stay moving is significant. And the same thing is true with air and a fan. And as we increase static pressure, we're going to reduce fan output. It's like increasing speed in a car. It's going to require a lot more fuel to drive 80 than it is versus 40. And we know that static pressure is not really uniform. The plot here in this shows the comparison of static pressure for a 60-foot wide house and a 50-foot wide house. And what we see is that 60-foot wide house really peaks at about 0.2 inches of water column, where the 50-foot wide house peaks at around 28. And it's essentially we're trying to force more air through a given area with a 50-foot wide house than we are in a 60-foot wide house. It's far more efficient to run high air speeds in a 60-foot wide house than it is a 50-foot wide house. And what's really interesting here is you can see where the fans are operating down here at the, say, 80 to 100% of the length scale. We've got some fans that are running at 0.28 when they're typically spec'd to run at, say, 0.15 or 0.10. So they're really operating well past where we would, quote unquote, expect them to act. Static pressure increases are unavoidable. We can't avoid the increase that occurs at the tunnel inlet, which are these steeper increases here. You see it around 20%. Those are the tunnel inlets. We can't get away from that. There's not a good way to improve that yet. Then there's obstructions. We have exposed framing. We have brood curtains that are in the way. We have feeders. We have drinkers. All these things that impede airflow. Friction on the walls. It's not a huge component, but it's there. And these are things, again, that we can't really control. We really set the static pressure characteristics of that house once the last nail or screw is driven and the builders walk away. That's where it's going to be, and there's not a lot we can do to change that. So really the only avenue for improvement we have is improving design into the future. And one of the interesting things that we found from this research is where a fan is in the house really dictates how it's going to perform. It's kind of counterintuitive that a simple change as in moving a fan 5 foot forward in the house would make a difference, but it does. And so these are real numbers that we measured on a house. And so fans 1 through 4 here on the top of this image, that's here on the far left of the plot at the bottom, 5 through 8 on the end wall, here in the middle, and then 9 through 12 on here at the tail end. And so what we see is that the fans that on average that perform the best are the fans here on the end. And that makes a lot of sense, right? So it's a momentum thing. Driving in a straight line requires a whole lot less energy than driving in a straight line and then making a quick turn. That momentum has got to be accounted for somewhere. You got to throw on the brakes and turn and slow down, and all of that takes energy. If you're going straight, it doesn't. And so what's really interesting here is when we look at the fan output, which is the blue line, we see the fan output for fans 1 through 4 particularly on the average, is much higher than fans 9 through 12. And the interesting piece there is that there's an access door right there. On the bottom right-hand corner of that top image, fan 12 is shifted one bay forward. So all the fans 9 through 12 are 5 foot forward of their counterparts on the other side. Just that one change, just that one very simple change, putting a door there, really changed. You know, we would expect this to be a mirror image of one another. We should expect that fan 9 should be roughly the same as fan 4, and it's not. It's not anywhere close. You know, we would expect that fans 1 and 12 would be a little closer, and they're probably about 1,000 CFM different. So again, a small change just introduced by door makes a big difference, and it makes a big difference in the pressures that those fans experience too, which leads to lower flow. And so fan placement effects are something that again are set once that building is stood up and the crew cuts holes in the wall and mounts fans. You know, the ability to change that is very limited. It's very hard to do. You know, one of the real practical aspects here is that we need a door to move birds and equipment in and out. You know, that precludes putting fans all the way across the end wall. There are some houses that have that, but you know, there's some practical applications here that we have to account for in terms of what fan performance can actually realistically be and be improved. When we look at distance from the end wall, we see a story here that really starts to develop and really illustrates this pretty nicely. When we look at the top, and these are two different houses. Static pressure, where about half the fans are on the back wall, we see static pressure doesn't climb much above 15. I think that 16 is the peak static pressure. However, when we have fans all on the sidewall, as in the plot below, our peak fan pressure is about 0.26. In terms of fan output, that is a huge change. And when we look at the rated output, which are the blue curves versus the red curves, you know, as that static pressure difference is lower, we see that those fans are going to perform closer to the lab values than when there's a significant departure. There's a big difference, particularly in the bottom plot, between the rated output and the measured output. And so that's around, you know, I'd say 23,000 versus 18,000. So we're looking at a 5,000 CFM difference. When we start looking at, you know, 10, 12 fans, that's a lot of lost capacity to remove heat. And that's, you know, that's where we start running into trouble, particularly with heat stress occurring even in sometimes cold weather, but certainly during moderate conditions when we have that big a deficit in terms of air movement through the house. And so when we look at where fans are and its effect on velocity distribution, the top plot is a 60-foot wide house, and all the fans are strictly and totally on the sidewalls. We see that fan end, which is on the right as you're looking at this plot, we see that dead spot there is much, much higher than the other two. When we look at the 50-foot wide house, we see the same thing. We do have some end wall fans there, and that dead spot is much lower. And then on the 40-foot wide house, we have fans that are on the end only. Now, again, the air velocity here is much lower, but it still bears out that fans that are on the end only, we don't seem to have that dead spot at the end of the house. Again, there's practical considerations there, such as being able to catch birds out of both ends of the house, move equipment in and out efficiently, that drive that. But you know, in the future, that may be one of our only options to help really improve velocity distribution, but also airspeed. We lose a lot of energy making those fans turn that air. We have some pretty significant static pressure spikes with those side-mounted fans. And so again, these are things that we're researching to try to find an economical way to make this work and maybe reconfigure the houses in some different ways to help get rid of end wall entrances. And this is a pocketbook issue. When we look at fans that are operating where they're spec'd and designed, which is usually around 0.1 or 0.15 inches water column, versus where they're more likely operating, which is at 0.2 or 0.25, we see about $25 difference per fan per year. It doesn't take long with 10, 12, 14, 16, even 18 fans on a house. As that average static pressure that those fans operate at goes up, $25 a fan per house per year, 6, 8, 12 house farm, that's a lot of money, just simply in lost electricity costs, where we're not getting a lot of benefit in terms of airspeed back out of that. It's just small incremental increases for a lot of energy input there. So that brings us to sort of the next point with static pressure and how it affects things is we start looking at flow obstructions. How do we improve things? Ideally, a broiler house would be completely smooth with nothing in there but chickens. But unfortunately, we have to feed them. We have to give them water. We have to provide heat. So those are necessary things we have to have in there. And so unfortunately, we can't get rid of those. And so we just have to deal with them and try to design around them as best we can. One of the big things that we did a lot of, say 10 years ago, was we were putting deflectors in the ceilings of broiler houses. That causes the top right plot there shows a difference, and there's about a 10% difference just from simple ceiling deflectors in terms of fan output. That's reduced capacity for heat removal. As I tell growers when I talk to them and visit with them about these things, that's really we're paying for 10 fans, but we're getting the benefit of 9. That's a large average wind speed reduction simply through just putting in obstruction in the house that we intend to help, but actually is hurting. But then there's also other obstructions that create dead spots. We look at tunnel doors, for instance. Those can really create some dead spots. And when we look at the bottom right plot there, when we think about design velocity, this house has 10 fans that run at X CFM, and we expect to have our air velocity be, let's just say, 600 feet per minute. A wider house is going to be more efficient at delivering that. That's the red dots there. We're typically at around 20% above design velocity for most of the house in a wide house. The blue dots are a narrow house. We are right on the line there. And of course, the 50-foot wide house is about the same. But what's interesting is regardless of the width of the house, we tend to always end up at around 25% of the house being below design velocity. And I think without some serious reconsideration of where we're putting fans and how we're arranging and designing cooling systems, we're going to be at that level. And so then we need to make sure that we're accounting for those differences as we look at heat stress and productivity and some other measures to see how we're actually doing. So a little bit deeper dive into the obstructions here. When we look at the 60-foot wide house, wherever you see lines that are really close together is where you see big changes, just like any other topographical map. And what we see up there is really we have a couple of spots, one around 125 meters and another one at right about 150 meters. You can see those very steep inclines. Those are curtains. Those are curtains that weren't tied up very well, but they're there. And that's a real world situation. We see those. We also see a static pressure spike there. When we look at the 50-foot wide house, this house has ceiling deflectors. Excuse me. And so that's why you see those little raindrop looking areas throughout that. We see the areas of high air velocity in the relative sense, and then you see the 2 dots on either side of that. And what that means is the air is slowed down and then it goes, it speeds up under the deflector and then it slows back down. And so the air is constantly contracting and expanding. Other than the localized increases, what we really see there is that air is slowing down continuously as it goes down the house. Rather than maintaining a fairly constant level like we see in the top plot, it's slowly but surely degrading and going down as it gets towards the fans. That's sort of a problem because we expect the deflectors to really help improve air velocity throughout the house. And really what we're doing is we're just making it harder on the fans to move air and remove heat. And then on the bottom, again, we have some pretty clear obstructions there. We have brood curtains, they're at about 30 meters. And then again, at almost 100, again, that's a fairly predictable type of place to see it and fairly typical type of response. And then there at about 65 meters or so, you see a spot there on what would be the bottom of the plot where you see an area of low speed, and that's a box heater. And and you see it also at 20, and you also see it just past 100. Those are box heaters on the wall. And so those heaters, they're sticking into the house, are fairly large, a couple feet square. And so that really slows air down around them pretty significantly. And so when we look at the other side, we talked a lot about where fans are and where obstructions might be, but one of the areas that hasn't received a lot of attention is the inlet design and how that affects cooling. Our ventilation capacity has been increasing, I'd say since our early research in the mid 2000s. When I first came to work at the lab, 550 feet per minute was a pretty fast house. Now we're looking at 1,000, 1,200 feet per minute in some cases in some areas of the country. But that requires more more fans, more pads, and we design to meet a particular spec. So we're not drawing water into the house, and we're at an efficient place in the pad's operation scale. And then of course we always add a little bit more because we have clogs, pads get dirty. But what that's caused is that we have big dead zones. Again, seeing this plot again, there on the left of that top plot, you can see that area. That's probably 75, almost 80 feet of a 60-foot wide house. That's a lot of floor area there where we don't get a lot of air velocity. And people make the argument, well, but that's where the pads are and the incoming air is cooler. Well, yes, but when the length of the pad system is 50 meters, what we see again, that last 1/3 to 1/2 of the pads towards the fan is where the vast majority of the air comes in. So we're not really getting the cooling effect I think that most folks would intuitively think that we'd have. And again, referencing that down to static pressure, it really starts to make sense where you see that really steep curve start to happen is where we really see a big difference there in terms of pad flow. Sorry about that. So we decided to measure it. We have a grower that we collaborate with a lot up in Sussex County, Delaware, and these houses were built fairly uniquely. They're built to be very high-speed houses. They're still big houses, 60 by 600 feet, 16 exhaust fans, and they've got 148 feet of pad per side. That's a lot of pad. The interesting piece of this is whenever we put tunnel doors in a broiler house, we typically look at, say, 16 feet, 20 feet doors. These were installed in 8-foot sections. And so that gave us a lot of flexibility to play with inlet length and how that affects things. And so this is a general sort of graphic of what that test setup looked like. So at 148 feet, the entire pad was open, all the doors were open, then we closed a door and ran the system and got velocity numbers, got cooling numbers, all the way down to 108 feet. And so I'm not going to present all the data here. I'm going to trim that down to just a few points that really make sense here. So when we look at the pad velocity profile, so that first edge of the pad there down at the far end, we see again very low, 1.5 meters per second, and then it goes up to 3 meters per second. In fact, goes up to almost 4 meters per second in some spaces. So we see this general trend along the pad from slowest to fastest being towards the fans. We see this pretty uniformly through all the data that we've taken. When we really look at the distribution in terms of length, and I'm going to talk about free pad lengths here, 148, 124, 108 feet. That general trend is the same. We're ending up at around 550 to nearly 600 feet per minute. Now remember, these pads were designed to operate at around 350. Much above that, we start to see air, water being driven into the house. And so, that first 50% of the pad, we're seeing that, but then the last 50% of the pad, we see those big increases. And if you're ever driving by a broiler house on a hot day, and there's big birds in there, you'll tend to see dry spots at the end of the pad closest to the fans. And the big reason for that is we're just ripping air through there a whole lot faster than what we actually intend to. And so we're evaporating more. And so what's happening is we're actually not getting the cooling that we get if we were all at the same airspeed across that pad. When we look at evaporative efficiency, this really starts to tell the tale. When we look at the trailing edge of the pad, so down at the far end, farthest away from the pad, we have, I'll be honest, pretty terrible efficiency there in terms of cooling efficiency for the long pad setup. When we were down at about 50%, when we design spec for 75. When we shorten that down, we take 24 feet of pad out, which is probably crazy to a lot of people. But when we take out 24 feet of pad length, we actually get improved. We get improved efficiency there, and we do even better as we go on down to 108 feet. So we took out essentially 25 to 30% of that pad length and improved cooling efficiency significantly. We look at the right plot. And I apologize, those labels aren't real clear, but the left is old pads, the right is new pads. Of course, with new pads, we expect improved efficiency. And again, there's just something magical about being at that far end of the pad with 148 feet that even with brand new pads, we're still at around 50%. The good news is that new pads give us about 10% more efficiency. And when I say new pads, what I really should mean to say is clean pads. Helps improve that cooling efficiency. And this is really sort of where the rubber meets the road. When we look at end-to-end temperature differences, old pads are in blue, new pads are in red. At 148 feet, we have a 4-degree Fahrenheit difference between each end of the pad. That's a huge difference, particularly when we expect it to be no difference at all. And even with a new pad, we're still at 3 degrees difference. And for a point of reference, we designed a broiler house to where from the inlet to the outlet, we see no more than a 5-degree temperature rise. The fact that we have a 3 to 4 degree temperature rise just along the pad section, that's kind of terrifying, honestly. But as we start to close at the pad, again, it doesn't make a lot of sense that having less area for cooling improves things, but it does. And so when we get down to that 108 feet of pad, what we see is that we're less than a degree Fahrenheit difference between the end, which is kind of hard to measure in this circumstance, but it's true. So we really have done a good job in doing that. And what's interesting about that data is that even in reducing that pad, we only increased the static pressure by about 2 points. So not great, but certainly not a earth-shaking difference. There are a lot of folks that thought, we go up quite a bit, and really, and when I say points, I mean 0.01 inch of water column. A lot of folks that we see pretty big increases, and then the concurrent reduction of flow, and we didn't really see. We saw some reduction, but not much. And so what we found, at the end of the day, is that face velocity really varies. It just about doubles along the length of the pad. But our efficiency is improved with a shorter pad run. And that's because as we start to shorten that up, that face velocity becomes more uniform. And so what that really means is shorter pad run and new pads really is sort of the gold standard. and what it makes this an easy thing to change in new designs is that we can get that same area of pad. We can just move from a 4 or 5 foot pad, go to a 6 foot pad. We have the sidewall real estate to do it. It's actually cheaper to go shorter and taller than it is to go shorter run with a taller pad than it is to do a longer run with a shorter pad. We're looking at say $125 to $150 per running foot of pad system, and that's really all the hardware, not necessarily the pad itself, and the installation costs. So it's certainly a way to improve things, and that's something we're hoping to get some measurements on. Hopefully by the end of this summer, while it's still hot, we've got some houses lined up to test that. And that brings us really to the last part of what I'm going to talk about today, which is evaporative cooling water needs. We don't typically think of the South, and particularly the Southeast, as having water problems because we tend to get more rain than other areas of the country in many instances. But again, changes in groundwater levels, increasing regulatory issues for wells really starts to make us rethink how much water we use. And of course, it's just better to use less water, in the aggregate. But knowing what total house water needs is you got to know what that is to make sure we have enough water when we need it most, which in this case is right now we need a lot of water for evaporative pads. We need some for bird water, clearly, but evaporative pads is our predominant use. And so we took another look at this and worked out what evaporative cooling water needs would be. So we took climate data from 732 stations from NOAA. And you can see there on the bottom right, they're scattered out all over the country. And our records range from 5 to 81 years. So our average record length was about 44 years. And so we had a lot of data to crank through and went through psychrometric analyses to look at evaporative efficiencies. And so what was really nice about that is we got to really look at what does this mean and not just sort of cherry picked points that may or may not actually be relevant. A lot of times when we talk about evaporative water use, we're using some kind of extreme disastrous conditions that even under a climate change or heat wave scenario don't really happen. And so this is the resulting map. And of course, where we see, from about I-35 in Texas, Oklahoma, eastward Arkansas, through Tennessee, Kentucky, North Carolina, Virginia, up into Delaware and Pennsylvania, we go from about 5 GPM per 100,000 CFM of ventilation capacity out to about 6.5. So that's a pretty good range there. For where we see most of, say, broiler production in Mississippi, Alabama, and Georgia, or anywhere between 5.6 and about 5.5. There were some estimates that were really, really high, and then there's some historic estimates that were just not enough. And this is again a little bit more accurate way to do this. Our typical ventilation capacities, to give you some scale, are anywhere from 250,000 to 500,000 CFM. So you can take 2.5 or 5 and multiply that by the numbers you see in the map and give you an estimate of how much you're going to need when the conditions are at their worst. What does that municipal water system need to supply to that farm? And so one of the things that we've seen is that now growers are starting to think about, okay, maybe we need to run a bigger pipe here. Maybe we need buffer tanks a couple places on the farm to help make sure we've got enough capacity on these really hot days and help spread out that risk a little bit more. And here on the right, it's just a very simple example for Laurel, Mississippi. There's a lot of poultry, a lot of broilers grown there. Simple example there, but what we end up with is that house needs about 14 to 14 and a half gallons per minute for one house. And so when we start looking at a 4, 6, 8 house farm, that's a lot of water we have to supply. And if our water system is not capable of that, then we need to have, get a buffer tank or some other supplemental source of water to be able to do that, to be able to provide that much to ensure that those birds are cool. Because without water, evaporative cooling does not work. And we're already in a humid climate where it's not, it's effective, but it's not great. And so we need to make sure everything's working as needed. So just a quick look into the future. As I referenced before, we're updating heat and moisture production design data. Data we typically use was published in '82 by scientists that were here at our unit. But again, given the changes in nutrition management and genetics, we're probably going to see some significant changes there. And then we're also looking at acute weather events, heat waves and cold waves, and seeing, okay, are our buildings designed to handle those types of events effectively? And if not, how do we need to change those in terms of capacity for heating, cooling, ventilation, to make sure that we can, effectively mitigate those types of situations. I want to give a quick thank you to my collaborators here that worked on all these different projects with us at the National Poultry Technology Center at Auburn University, the folks there, folks at Mississippi State and at the University of Wisconsin. We've all worked together for many years and worked together on these projects. And so I really appreciate what they've done to help generate this data and hopefully help out our stakeholders. So with that, any questions?
Thank you so much, Dr. Purswell, for that. It was very interesting research and very helpful information. If you, just a reminder, if you do have questions for Dr. Purswell, please submit them through the Q&A option, and we quickly go over them. If we can't go over all questions today, your questions will be answered and will be posted on the landing page for this website. In the meantime, I do have a quick question for you that was submitted directly to us. When are the most challenging conditions for broilers under heat stress? I know you talk a little bit about this, but would you expand on that?
Sure. We typically think of heat stress happening in the summer. The truth is, for a broiler house, it can happen throughout the year. In fact, we have heat stress situations in December and January and February, and they can be significant. I mean, I think, traditionally we think of July for most of the broiler belt is the worst month. And that is true in terms of just sort of frequency. In terms of severity, it can happen at other times of the year. Really, when we see, that recovery period at night, when temperatures stay high. I know that last week here, for example, heck, we had nighttime temperatures that were above 75 degrees Fahrenheit, with a daily high of around 100. That's significant. When we had that for 4 or 5 days straight. And so it was really, really challenging. And we have birds here on our research farm. And so that was a pretty tense 4 or 5 days there. Whenever we see that, nighttime temperatures don't get below 75, that's always sort of a red flag. And even for our red meat counterparts, that's the same thing. I also say when conditions are a little milder, say mid 80s, and we don't get below, say, 70, where that differential between high and low for each 24-hour period, if it's less than, say, 15 degrees, then that's when we're going to have a particularly challenging day. The weather conditions just won't allow for it to cool off enough at night to really help the birds rebound. So I would kind of give a simple rule of thumb here. If your overnight predictions are not the difference between your daily high and your nighttime low, or not more than 15 degrees, that's when you should go out and take a look at the age of your birds, the size of your birds, and think very seriously about turning on some extra fans just to make sure they get enough recovery ventilation to forestall any issues later the next day. It really helps them bounce back a whole lot better. It leaves a whole lot more physiological capacity to deal with heat stress the next day.
Thank you so much, Dr. Purswell, for helping us understand those conditions. That's very important. So I don't see any additional questions, but don't forget that you can always reach out if you do have questions after this webinar. Dr. Purswell is part of the, sorry about that. He is part of the ARS Poultry Research Unit. So you can always reach out to Dr. Purswell directly, or you can contact me at maribel.alonso@usda.gov. Thank you for joining us today. Our next session is on August 10th from 2 to 3 p.m. Eastern Standard Time. All sessions are recorded and will be available for viewing at the webinar's landing page. And I'm going to add that to our chat option here on the side so everybody can have that information. Thank you, everybody, for joining us today. Have a great afternoon.